All right, so let's get started with our proofs for today. You guys, again, proofs are not scary. I know you guys think they are. But before we even get into proofs, I want to go back to probably either middle school or upper elementary, and we're going to relearn some new, not some new terms, but we're going to revisit some old terms. So let's begin off here with these different properties. You guys remember learning about these? The reflexive, the symmetric, the transitive, the distributed.
Can you turn off?
Okay, most of you probably not. And I know they might talk about these in Algebra 1. I know I typically don't. But it's actually not that bad. We talk about reflexive, symmetric, transitive, and distributive. So all we're going to do today is we're going to relearn these different properties. Oh, they moved closer.
Leave it.
What's the issue with it?
Oh my,
There you go.
What is wrong with
Right there.
you?
All right. So guys, when we talk about reflexive, the easiest way for me to tell you what the reflexive property means is that basically what you see is what you get. And all it really says is that something is equal to itself. Therefore, an example of that would be A is equal to A. That's it. That's all the reflexive means. Something is equal to itself. So when you have the same thing on both sides of the equation, we call that the reflexive property. Not to be confused with the symmetric property. With the symmetric property, we're going to go from having one equation in the reflexive to having two in the symmetric. So in the symmetric, we start off by saying that if A is equal to B, then B is equal to A. So what did I do there? Joey? Yeah, just flip over the equation. Switch sides. Okay, so that's the symmetric property. Yeah, conditional statements, yeah. Basically, symmetric property is when I take an equation, I just flip it. That's all the symmetric is. The transitive is a little interesting. Because a lot of times students look at the transitive and they think substitution. And it kind of is, but it's a little more than substitution, right, Taylor?
Yeah.
Okay. So let me start off by saying, or by listing that A is equal to B and B is equal to C. What conclusion can you get? A is equal to C. So if two things, in this case A and B, or A and C, are equal to the same thing, they're both equal to B, then therefore they are equal to each other. Okay, so that's going to be the transitive property. All right, you guys should already know the distributive property. And that is that if I have A times B plus C, what does that equal? AB plus AC. That's the distributive property. And these are going to be the reasons that we're going to put down in our proofs later on. And now we have some new ones that we need to talk about. So again, these ones you guys should have seen before, whether you remember it or not, but they are things that you should have seen before. So let's move to some that you haven't seen before. And that is identities versus inverses. And notice the terms are slightly different. It's the additive identity. What does that imply? What operation? Adding. It's addition. All right, so identity. When you're dealing with an identity, it means that the value is not going to change. So what do I add to something to keep it the same? 0. So the additive identity property says that A plus So what's my multiplicative identity? What do you multiply something by in order to get it to be itself? 1. So your multiplicative identity is a times 1 is equal to a. So anything times 1 is itself. Anything plus 0 is itself. Alright, now let's take a moment here and let's discuss inverses before we actually define the additive and multiplicative inverse. Okay, we have our 2 problems up here on the board, right? Alright, and when we look at this, we look at Dylan's beautiful work over here on the right side of the board. What did Dylan do to get rid of this negative 47? Added it. So what did it do? So what do we say that does? Cancels out, right? So when something cancels something out, that's called its inverse. So what's the inverse of multiplication?
Division.
Division. What's the inverse of square roots? Oh, come on, guys. What do we use to cancel out a square root? Yeah, well, which exponent?
Squared.
Squared, yeah. Square roots and squares cancel each other out. Cube roots and cubes cancel each other out. They're inverses of one another. So what do I do for an additive inverse? What do I have to add to a number in order for it to cancel out? The negative of that number. And therefore the additive inverse says that A plus a negative A equals 0. So again, when we're canceling out with addition, what are our goal values to get to 0, correct?
Yep.
What about for multiplication? What's your goal for multiplication? Cancel out to what? 1. So in multiplication, the cancellation is going to give us a 1. So what do I have to multiply A by in order to get to 1? Okay. Then they'll give me A squared.
So you'd have to do the opposite of a squared.
Would you have to do 1? Well, what's A?
Okay, let me ask you this. Oh, hold on. Let's try this a different way. What do I multiply 3 halves by to get to 1?
2/3.
How are those two things related?
Because then you just cancel out.
It's the reciprocal. So what is the reciprocal of A? 1 over A. And guess what? If you're multiplying by 1 over A, what are you essentially doing? Dividing by A. Okay. So again, this is all stuff you guys do all day long when we actually solve equations. I'm just asking you to be a little more aware of what's going on. And then, of course, we have our normal addition, subtraction, division, and multiplication rules that take place. So let's do a little bit of fun, very quickly. I want you guys to tell me what property is being demonstrated.
Okay.
So we actually have 4. We have 4 of these right here. Again, we're just looking at those 4. You guys have to tell me which property is being modeled with that statement. All right, number 1, Kylie. That is symmetric property. Well done. Again, we know it's symmetric because we look at our first equation here, and we switch sides. The 3x minus 4 goes to the left, the 5 goes to the right. That's symmetric property. Number 2, if angle 1 is 90 and angle 2 is 90, then angle 1 must equal angle 2. Lindsay, which property is that? That's the transitive property. Look at number 3. You might ask yourself, okay, what changed? How did it change? So on number 3, the measure of angle 1 plus 30 equals 90. Then the measure of angle 1 must equal 60. So Gavin, what happened on that one? Gavin, this is one of those others. You might be thinking of something more complex than it needs to be. How do we go from angle 1 plus 30 equals 90 to angle 1 equals 60? What do we do? We distributed it. What changed? What's missing? So again, think about this side over here. What's missing from this side to this side? All right, Taylor, help us out a little bit.
It's the additive inverse.
Of what?
What? I mean,
What are we using? What are we trying to cancel out the additive inverse?
oh, the positive 30.
Positive 30.
Subtract
Yep.
30 from it and gives us a 60.
Okay. In this case, I'm completely okay with just simply saying subtraction. Because you're going to subtract 30 from both sides, and therefore the subtraction property. Okay? Alright, last one. Shannon. 5x equals 15, therefore x is equal to 3. That would be your division property. Okay, any question on those properties? Alright, Joe, you still with me? Alright, Tiffany.
Okay, so I understand transitive, but why is number 2 transitive when there's only 2 adverbs?
Since angle 1 and angle 2 are both equal to 90, then therefore they are equal to each other.
So there doesn't necessarily have to be a C.
No. It can be two things equal to the same thing. They're equal to each other. Well, let's get into proof.